Morning all. Morning Tanishka. Good to see you online. Cool. So part 3 of Physics 1. We've looked at sort of different types of energy. We've looked at the transfers, and we've been through quite a bit of that over the past few lessons. So I'm not going to go back through much of that again now. I know last lesson we did quite a few calculations, and we're just putting together some exam questions at the moment that we're going to upload onto Google Classroom for practice over half term. So bear with us on that one. I think one of the other teachers putting that one together, but I'll double check on that a bit later on. Now, what I want to do today is we started looking at the specific heat capacity last time round. Morning, Amy. Started looking at specific heat capacity last time round. What I want to do is talk about the required practical. So we'll go through what it is, how it works, some of the calculations that goes with that. We're then going to look at efficiency, and we're going to look at Saggy diagrams, because students always find Saggy diagrams quite tricky. And then if we've got time, we're going to finish with renewable and non-renewable energy types. Now, just an aside on this one, I'm just putting something together at the moment I want to try with some of you. Not to replace these videos, because I want to keep going so we build up a bank of them. But I want to have a go after half term and do a Google Classroom meetup. So if we can get enough of us online, morning Chris, actually have a bit of a face-to-face Q&A session. So if you guys are up for that, morning Michael, if you guys are up for that, let me know, and I'll use you as a bit of a trial class so we can sort of try out some techniques before I train up some of the other teachers in school. So we'll see how that goes anyway, but I'll keep you informed as we go. So what we looked at last week then, to start properly now, we looked at this idea of specific heat capacity. Now, if you can remember back to the definition, I don't know why I'm writing on today, specific heat capacity. If you can remember the definition for this one, it was the amount of energy required, so the energy that's being transferred, and remember this little triangle just means the change in energy, to raise the temperature of 1 kilogram of a substance by 1 degree Celsius. So we've got a change in temperature as well. Now, this sort of C is the specific heat capacity itself, and the units that we use is joules per kilogram degree C. And it's probably one of the more complicated units. Morning, Olivia. It's probably one of the more complicated units that we actually use with this. So take a bit of time to get your head around what's going on with that. So we said that we looked, I think water was one of the main ones we looked at last week. Oh, sorry, last week. What's today? Wednesday, Monday. We said water has a specific heat capacity of 4,200 joules per kilogram degrees Celsius. And what this means is that if I have a kilogram of water, I've got to transfer 4,200 joules of energy in to raise the temperature by 1 degree Celsius. Now, water is quite high. Most other substances are much, much lower than that. Even when you look at cooking oil, in order to raise the temperature of cooking oil, it's hugely lower. So we need to provide a lot less energy in order to heat it up so we can actually cook food with less energy at a higher temperature. Now, one of the required practicals that you need to be able to do when in order to be able to, to explain specific heat capacity, and there's quite a few YouTube videos on this, so I'm not going to sort of demonstrate in any way, but we'll just talk through how to do it, is we need to be able to measure the specific heat capacity or calculate the specific heat capacity for a given substance. Now, the method for this one, whether we're looking at solids or whether we're looking at liquids, is pretty much the same. What we end up with, let me just move that up a little bit. What we end up with is a container or a block at some point. I'm going to do this for a liquid, and I'll sort of talk about how we can adjust it. So we've got some form of container. This is just going to be a beaker. We're going to have some liquid in there. Now, I'm going to put liquid, and we need to have a known mass. If this was a solid, it could just be a solid block. But what we're going to put into here is we're going to have a heater of some sort. So I've got my heater. And we're going to have a thermometer. Because we need to measure the temperature change. Morning, Chris. So what we need to measure now is some way of calculating the energy that has been transferred into that heater because then we know the energy that's been transferred to this liquid. So what we would do with this is we would have some form of power pack. That would be attached either to a joule meter, if you're really lucky, because that means we don't have to do very many calculations. If we haven't got a joule meter, we would connect it to an ammeter, and I'll show you the calculations with this one. And we would have a voltmeter as well. Okay, so we can either have a joule meter to measure the energy directly, and that will just tell us literally the amount of joules we've supplied to that heater, or we could have it connected to an ammeter and a voltmeter. And the other thing that we're going to need is some form of stopwatch or timer. Okay, so we need some way of timing this. Now, as I said before, the actual practical and describing what to do, even this would be a sort of 6-mark question in the exams. Now, you'd be able to get 4 marks on this just to describe the process, even if you couldn't remember the calculations. And what we would do is we would measure the starting temperature of the liquid or the solid. We would then turn our heater on. We would measure the energy that's been transferred, and we would time how long we've turned it on. Afterwards, we would record the time, and we would record the energy change. And what we could then do is plug this into this calculation here. Now, if we need to know the energy, because actually, if I rearrange this equation, let me just show you how to do this. The energy transferred is the mass times the specific heat capacity times the change in temperature. So in other words, the specific heat capacity, which is what we want to calculate, is going to be the energy transferred divided by the mass times the change in temperature. So I need to know these 3 things in order to be able to calculate the specific heat capacity for that substance. So this is the one that we haven't done yet, and there's a couple of ways of doing this one. Like I said, the easiest way, if we're lucky enough to have one, is we can actually use a joule meter. If we don't have that, what we can do is use some of the calculations that we have last time, and we can then calculate the energy transferred. So let me just move over here and talk about power for a moment. So power is a term that it tells us how quickly we're delivering energy to something. So we measure it in watts. Now, 1 watt is the equivalent of having 1 joule of energy being delivered every second. So if you have a look at your, pretty much any electrical appliance you've got in your house, somewhere on there will be a power rating. So I think my laptop, if I look at the adapter on that one, it's got 45 watts written on there. That means that every second my laptop is charging, it is using 45 joules of energy, and it is transferring that energy into the laptop. If you look at things like kettles have a much, much higher energy rating, because as we went through a minute ago, water requires huge amounts of energy to raise it by 1 temperature. And most of the time we're taking water from the tap, which may be 10 degrees, sometimes even a little bit lower, and we want to bring that up to boiling. So we're having to increase the energy by maybe 95 degrees Celsius. So if we're boiling a kilogram of water with that one, we've got 95 multiplied by 4,200, which is a huge amount of energy. So when you look at your kettles are generally anywhere between 1 kilowatt and 2 kilowatts. So that means that every time, if we've got a 2 kilowatt kettle, every second that it is turned on, we're transferring 2,000 joules of energy. That's per second. So it gives you an idea. And you can have a look at your kettle, somewhere on there, it'll be written what that power is, and you can calculate the energy that's being transferred if everything's working as it should do. So the formula for power is energy, and this is the energy that's being transferred. We can also call this work done, and work done again is the energy that is being transferred for a particular purpose, and that's in joules, and that is divided by the time in seconds. So if we know the power, we can work out the energy, assuming we know how long it's been turned on for, because our energy is equal to power times time. There's lots of formulas this, and as I said last time round, The best way of getting good at formulas is just to use them. And you can do these sorts of calculations. Go and pick up any electrical appliance in your house. If you play a games console, written on the games console, there'll be a power written down somewhere. So you can actually work out how long you've spent playing that console in any one particular gaming session. Work out the number of seconds. Turn the kilowatts into watts and do this calculation here. And you can work out how much energy that's been transferred. So it's an easy calculation. So you can do this with pretty much anything, even mobile phones, how long you've been charging it for, how long has it been transferring energy. And you can work out this energy and get used to using these calculations. Now, as I said before, we put a voltmeter and an ammeter in there because actually we may not know or we may not trust what the power rating is on our heater. So in this case, what we're going to do is we're going to use a slightly different formula. So in this case, we're going to do power equals our voltage, so our potential difference, the reading on our voltmeter, multiplied by our current, which was the reading on the ammeter. So we can get our power rating there. And if you want to be really good at this, I'm going to combine these two formulae, okay? Because actually, what we know is that power equals voltage times current. So if we want to work out our energy, what we can do is go voltage times current times our time. And that will give us this value here. Okay? So let me give you an example with this one then. And let's use our water, so our kettle, as an example for this one. Now, let's have a look. We've got our kettle. I'm going to keep the maths fairly simple for this one. And we're going to say we've got 1 kilogram. In fact, let's not say water. Let's just say we've got 1 kilogram of an unknown liquid. And we can go through and we can work it out. We're at home, so we're probably transferring. That's plugged into the mains somewhere. So we're going to be looking at 230 volts because that's what our mains electricity going into the house. And although we haven't done electricity yet, if you're in year 9, you probably haven't done this yet. You do need to remember that value because that's what the UK is. If you go into other countries, so you go to America, America will work on 110 volts. So it's worth just having that and being aware of that. Now, in terms of current, what should we go with this one? I've got my calculator open, so I'm just working out these ones as I'm going along. So we're using, let's say it's a 2 kilowatt kettle. So my current is going to be about 8.7 volts on this. Just literally working out these calculations as we're going along here. So, and again, this is the sort of thing you can do. We can use some of these calculations and we can actually come up with some examples. So 8.7 amps. So my kettle is going to be turned on for 30 seconds. So I'm going to time it for 30 seconds. My starting temperature, it came straight out the tap and it was 8 degrees Celsius. After 30 seconds, the temperature went up to 40 degrees. So my change in temperature, 32 degrees Celsius. Okay, so I'm literally, and again, this is, as I've said this a few times, you can do this at home. I'm making up this data as I'm going along, just so that I can practice using these calculations. Okay, so we want to calculate the specific heat capacity of this liquid. I don't know what the liquid is. I've deliberately making this data up so that I can't, so we can go through and we can find out. We set up here that C equals the energy that's been transferred divided by M, multiply that by our change in temperature. M is 1, and my change in temperature is 32 degrees Celsius. Remember we said that whenever we do any form of calculation, we want to do the 3 S's. We want to scribe, so copy the formula down. we want to substitute in any of the data that we've got. So I'm substituting in the data as I'm using it. And then I want to try and solve it. So what I don't know at the moment, because I haven't calculated this, is I don't know how much energy I've transferred. So I could, if I wanted to be really clever, and I'm not going to do this now because it will look really confusing, I could transfer in the formula that I'm going to use over here, and I could just copy this down for the top of this one, but I think that may look a bit confusing. So let's just do this a slightly different way. Let's write this formula down, and remember, in an exam, if I've got any question that needs 2 formulae, it's going to be worth a minimum of 5 marks. So there's huge marks available here if we can do it. So the change in energy is the voltage, which I said was 230 volts, multiplied by my current, that I said was 8.7 amps, and I had it on for 30 seconds. So if I plug that into my calculator now, 230 multiplied by 8.7 multiplied by 30. So that means in that 30 seconds, I'm going to be transferring 60,000 joules of energy into my kettle. So I can now go through and I can get rid of this E. And I can substitute in my value. So 60,000. So what I should end up with 60,000 divided by 32. So let's work out what this specific heat capacity is going to be. Divide that by 32. And C equals 1,876 joules per kilogram degrees Celsius. Okay, I'm not going to spend ages going through loads of these because we did a few calculations. The main thing is that you can use and you can describe how to do a practical. Even if you can't remember the calculation, you would be getting some marks. So I'll just talk through that, and then if you want to go through the calculations, you can watch this again afterwards. That's fine. So I've got a solid or a liquid. In that solid or a liquid, I have put a heater and a thermometer. I am going to turn the heater on. I'm going to record either the energy transferred, if I know the power, or if I've got a joule meter. If I don't know those, I'm going to record the current and the voltage. I'm going to turn the heater on for a known amount of time, and I'm going to record the temperature change. So I need to know the temperature at the start, temperature at the end, so we can work out the temperature change. I'm then going to use my calculation to work out C. And again, if you can do the rearrangements and if you can remember that, that's brilliant. V is potential difference, Tanishka. It's voltage. So we measure potential difference in that. We'll spend a lot more time going through the electronics side when we do physics 2, which is all about electricity. So I don't want to go through it too much, but again, it's another one of those overlaps between topics. The more you can understand one of the topics, the more you can understand the others, but it's the voltage. Okay? And like I said before, either during, probably afterwards now, I will run a trial of a Google Classroom meetup. So we'll run Google Meet, and we'll see if we can have a face-to-face, and you can ask any questions you've got, and we can just see how it works. So we'll do that at some point in the very near future as well. Brilliant. Now, it's worth noting on this one, there's a few limitations with the method as I've drawn it here. So I'm just going to put limitations down. What we often find when we do this one is that the value for C that we calculate, so if I put calculated C, is often too high. The reason is, as we're transferring energy to that block and it starts heating up, or to the liquid, the temperature of that liquid becomes higher than all of the surroundings around it. Now, as you know from the lesson I did on Friday and on Monday, if we've got a temperature difference, energy, particularly thermal energy, is going to move from where there's lots of it to where there's not very much. So what we start doing is we start heating up this substance, and the energy starts moving from that substance into the surroundings around it. So we're actually heating up that area as well, which means the temperature change is different to what it should be. Okay, say too high, sorry, it's often too low. But we've got this difference here. So one of the things we can do, so I'll tell you what I'll do, just so I don't confuse things. Let's just put is often inaccurate. Okay? So what we should do in an ideal world is we should insulate it. Because if we can insulate around it, and we can talk about the conduction, the convection, the radiation. So realistically, if we want to go properly overkill on this, we would want this whole system completely sealed with a vacuum, with some insulation material, with a shiny surface. Because if we've got a vacuum, we're going to stop conduction and convection. We can insulate around that. And then if we've got a shiny surface, we're going to reduce heat loss by radiation. The more we can do that, the more accurate the value for C is going to be. Okay, so just quickly again, as we're heating it, it heats up. The temperature of that is greater than surroundings, so we start transferring heat energy to the surroundings as well. So we don't actually end up with an accurate temperature change. So it's worth bearing that in mind, because this is where they'll often try to pick up additional marks. They'll turn around and say the true value of this. So say you calculated the temperature change should have been 32. And they go, the true value of this should be such and such. Or they'll turn around and say, your calculated value of C was out by however many degrees. What could be the reason for this? And you'd have to explain that actually some of the energy transferred to that substance was lost to the surroundings. So the change in temperature wasn't accurate. Okay? Hopefully that makes sense. So, let's go on to the next bit then. What I want to have a look at is efficiency. Just move my notes on. There we go. Now, efficiency is a topic that comes up in all three areas of science. We're going to be looking at it with some specific examples, and we're going to be doing some Sankey diagrams, because I think students often struggle with Sankey diagrams. But efficiency is basically how much useful substance or energy you're getting out compared to what you put in. So the more efficient we are, the more of our effort, the more of the work done, in a chemistry terms, the more of our product we're going to be getting from whatever the input is. Now, from a physics point of view, when we're looking at energy, the calculation we're looking at for this one, now I'm going to put it down as a percentage, so I'm going to multiply it by 100, but we could keep it as a fraction, is going to be the useful energy out and that'll be in joules, divided by the total energy in, because I've got joules on both sides, they're going to cancel each other out, and I'm going to multiply that by 100, because that's going to turn it into a percentage. With this, if you ever get a value over 1 before you multiply it by 100, or over 100% after you've multiplied it, you have done something wrong with your calculation. Because when you're looking at energy, you cannot get above 100% efficiency. It means something has gone wrong. And normally what happens is you've multiplied the two the wrong way around. So it's worth keeping that in mind. Lots of students don't like getting fractions when they're doing this, even though you're allowed to use a calculator for the calculations. So they'll always, so a lot of students would default to always divide the larger number by the smaller number, because it feels better for them. But it gives them the wrong answer. So if you get a value above 100%, you've made a mistake somewhere. Okay, so let's have a quick look at this then. What we're looking at doing is we want to work out why efficiency is important, why are we talking about it, why am I spending time teaching you? I suppose the simplest way is to think about when we're at home. Now, So I'm about to, once we can actually get people around to do the work, I need a new boiler fitted. So I'm going to use that as an example to start off with. So there's a couple of reasons I need a new boiler fitted. So let's just work out, I've got my boiler. My boiler is heating both the hot water, and in the winter it's my heating as well. So what I've got going in, I've got gas coming in. And not everyone uses gas. A lot of people use electric only. But I've got gas coming in. There will be some electric as well, because that's how it's all going to be controlled. And when that boiler is turned on, it will have a heat exchanger in. The water is going to be running through that heat exchanger, and the gas is going to be burnt to create flames, and those flames are going to be heating up the water. And that's what's going to heat up, give me the hot water, and it's also what's going to increase the heating. Now, the reason I need my boiler replaced is, one, they stopped making parts for it back in the 90s, but two, my boiler is only about 55-ish% efficient. So that means that 45% of all of the energy that I transfer into my boiler, so I've got chemical energy going in here, and we looked at where the electricity comes from in one of the previous lessons, so go back and have a look at that if you need to. But 45% of all of the energy that I transfer into my boiler is wasted. Now, the new boilers are about 97%, which means I can get exactly the same performance, but I only waste 3% of the energy. So more of the money that I'm spending is going to be going into the heating. So realistically, I should be spending a lot less money. So in the long run, it's going to save me money. And when you guys leave school and you go through and you get jobs and you start getting houses, these are the sort of things you need to look at. Now, what I could do is I could work out the payback time. And payback would be, if I look at the cost of having the boiler fitted and I work out the amount of the amount of money it's going to save me year on, year out, the payback time is usually in years, but it's the number of years before the cost has been repaid. So I'm just going to put recovered. So in other words, if it saved me £200 a year, and I don't know what it's going to work out, I haven't even looked at that, the payback time would be the amount of years it's going to take before I've repaid the cost of the boiler and the fitting. And you can look at this with lots of things. With double glazing, for instance, double glazing does save quite a bit of money compared to single glazing. But it also costs a lot of money to have installed. So you would be looking at then, how much money is it going to save in terms of the heating? How long will it take to recover that? And obviously what you will also be looking at with things like this is other features as well. In my first house I ever bought, we wanted double glazing fitted, but not because of the efficiency saving, but because of the increased security. So one of the reasons we do this in science, and one of the reasons why science is so important, is you need to be able to make these informed choices so that you don't get some salesman come around and basically sell you something you don't need and don't want and waste lots of your money. Because actually there's lots of people out there that do that because they don't have the necessary skills to make those decisions. Okay? So we've got the payback time and we've got this idea of efficiency. Now we can sort of put this into a type of diagram. So I'm going to just drop in some graph paper for a minute. This is generally when people start groaning, because a lot of people for some reason don't like graphs. It's going to work. Yeah, there we go. So I've taken this from another website. Hopefully they won't mind, but I've yet completely stolen this. Let me just move that over a little bit. There we go. So that we can use it. Now, I'm going to carry on using this new boiler as a bit of an example. So let's just put some data down here so we can start trying to use this in our graph. So this is going to be a Saggy diagram. So I'm going to put in, and I'm going to make up these values as we go along, because again, I want you to see that if you want to practice this, it's easy enough to do at home, to make up data, to put something together, to see what happens. And then you can always send it to me to check if you want to, or you can check it with each other. So let's say I'm going to put in 500 joules of energy. In the grand scheme of things, it's not very much, but it gives me an idea for this one. So bring that up. Fine. With my current boiler, that means my useful energy out, and this will be the amount of thermal energy that's transferred either into the hot water or into the heating system, is going to be 275 joules of energy, which means I'm going to waste the rest of it. So what's that, 225? to give us an idea. Now, what this Sankey diagram is, and I'm just going to change colours so you can see to make it a little bit clearer on here. Let's go with blue. What the Sankey diagram is a graph that accurately represents the energy transfers. So it's going to show the total energy in, it's going to show the total energy out, both useful and wasted. Now, the really important thing with this, and I'm going to put this here, it's the width of the arrows, not the length, that's important. The length of the arrows that I'm going to be drawing have absolutely no relevance in any way, shape or form. Now, you're probably looking at this going, right, you need to get on with it because I haven't got a clue what I'm talking about. Brilliant. So, what we're going to have a look at then is we're going to say that each square here is, let's go with 25 joules. So, I'm going to do 1 square equals 25 joules. Now, that means I'm going to have 20 squares. I had to think there for a minute. God, not enough coffee yet. 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18, 19. Right, I should have an arrow. So the width of this arrow is 20 squares. So 20 squares should equal 500 joules. This is my energy in. Okay? Do put questions in if I start becoming unclear with this one. I'm going to do a couple of these so you can see these as examples. Now, I said the length of the arrow is not important, so I'm just going to draw an arrow length. We always have the useful energy going horizontal and the wasted energy going vertically down. So this is going to be my useful energy out over this side. So that's useful. That's total. And waste, as you'll see in a minute, goes that way. So, again, it's the width of the arrow that's important. So I need 275 joules. So we're going to have 2, 3, 4. Oh, hang on. Let me just go. There we go. I'll put that there for a minute. So, if you notice, I've just drawn this arrow now. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That should be 275 joules. So we've got 275 joules. Turn it into an arrow. And the arrow makes no difference where it is, because it's the width of the arrow that's important. I'm not worried about anything else. Now, I now need an arrow that is 9 squares, okay? Because 9 times 25 is 225. So go 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm just going to join this arrow up here. Okay. So 9 squares equals 225. And that one's 11 squares. Now, all of this should add up to your total in. If we have additional squares, if we have different amounts of energy, we have made a mistake somewhere, because remember, we cannot make or destroy energy. So all of this should add up to whatever we started with. So I started with 20 squares and equaling 500 joules, because 20 times 25 is 500. Now, this arrow should be 11 squares, because 11 times 25 is 275, which we said was our useful energy. And this one should be 9, because 9 times 25 is 225. If I double check, 9 plus 11 is 20, and 275 plus 225 is 500. So all of these numbers should add up. I'll go through it again, Tanishka. It's not a problem at all. This is difficult, okay? It's the purpose of a Sankey diagram is a graphical representation of efficiency. And it's done in the same way as we do a normal graph. So what we do is we have to work out a scale. Now, my scale in this case was that 1 square was 25 joules of energy. So what I worked out was, if I started off with 500 joules of energy going in, I would need to have 20 squares, because 20 times 25 is 500. So I drew an arrow that was 20 squares wide. The length of the arrow is not important, so I just drew an arrow coming out. But the width of the arrow is. So my next arrow going out was my useful energy. So this is useful. And I said that 275 joules of energy is how much useful energy my boiler was putting out. So because it was 275 divided by 25 means I should have something that is 11 squares. So this is 11 squares wide, because that then represents 275 joules. I had 225 joules being wasted, so 225 divided by 25 gives me 9 squares. So this arrow had to be 9 squares wide, because it's the width of the arrow, not the length, that's important. Once we've worked that out, we just join them up to make them look like arrows. Right, I'm going to do another example with hopefully what my new boiler is going to represent, so you can see the difference, and I'll talk through it again. So bear with me on this one. Now, let's move this down. How big? Okay, so let's go down, and we'll start down here. So, new boiler. I'm going to go with 95% efficient. So if I put in the same 500 joules of energy, that should mean that so that's total in. My useful out should be 475 joules, which means my wasted out equals 25 joules. Okay? Now, if I go with the same scale I had before, that should equal 19 squares, and that should equal 1 square. So let's see what this looks like if that is 20. So let's see what this looks like on a graph. I'm going to drop my graph paper back in again. Sorry, my son's creeping past. Trying not to disturb anyone. He's sort of tiptoeing past. It's quite funny. Brilliant. Right, let's have a go at this then. We said we want 20 squares, so I need an arrow that's 20 squares wide. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18, 19, 20. So I have an arrow that's 20 squares wide. Length of the arrow is not important, so I'm just going to draw an arrow coming out. My next arrow I said needs to be 19 squares, so let's go ahead and put that in. 1, 2, actually it should be down to here. If I've lined up properly, good, that's 19 squares. And I'm going to turn that into an arrow there. My next one is only going to be 1 square wide. And I can make this arrow as long as I want to. It makes no difference at all. But it's only going to be 1 square wide because it's only got to represent 25 joules. Okay, so join all it up. Let's have a look. So that's 20 squares. I'm putting, you don't need to write this in, but I'm putting it in so you can see. So that's going to equal 500 joules. And that's my total in. This is my useful out. So that's 19 squares. And that's going to equal 475 joules. This is my wasted out. That's 1 square. And that equals 25 joules. And if you look at the difference between the two graphs, you can see that the width of this arrow is much, much greater than the width of this one. So the new boiler is much, much more efficient. If we go and have a look and compare that to this graph, this arrow is much narrower here than this one. which means it's less efficient. And we can have multiple arrows coming in and out of these, depending on what data we get given. And there's lots of graphs out there. If you go and Google Sankey diagrams, you can see these. There is huge amounts of examples. And if you Google Sankey diagram questions and put GCSE in there, there'll be people that have given you data that you can work with. Or, as I've just done, you can make up the data to suit you. So I think what I'll do, how much time we got? 20 minutes. I think what I'm going to do... Okay, so 95% efficient, Tanishka, means that 95% of all of the energy transferred has a useful purpose, which for me is heating up the water in my house. So it means 5% is wasted somewhere else. And that could be in the wires, it could be producing light, it could be producing sound, it could be all these sorts of other things, but it means it's wasted energy that hasn't ended up at the end purpose. Let me do one more example with this, and again, I'm going to make up the data just so that you can see and you have an example. And this isn't a true representation at all, it's just going to literally be off the top of my head with this. So let's imagine we've got a mobile phone. Now, I'm going to put in, and I'm going to keep it really simple, I'm going to put in 100 joules of energy. Out of that, we're going to end up with, let's say 20 joules of light. I'm going to end up with 10 joules as sound. And let's say we're going to end up with 20 joules. I'm just going to put other, because this is basically going to be the mobile phone working out how to do things. So that's given me 50. And I'm going to end up with 50 joules of heat. Those of you with phones, you know that actually when you got your phones on and using it a lot, it gets quite hot. But actually, we don't want our mobile phones to get hot. It's a completely useless form of energy. So these three here are useful. And this is wasted. Okay, and this is my total in. So you can see that actually with the efficiency, if you did the efficiency calculations, this particular mobile phone is only 50% efficient. So that's not particularly good. But for the sake of what I'm actually doing here, it's absolutely ideal. So let me drop my graph paper back in again. Wrong one. That one there. Unsupported image. Really? I've just done it once. Okay, let's do something. Try something different. Gotta love it when technology doesn't work. There we go. Let's try that one. Sorry about this. There we go. Brilliant. Okay, so let's go back and have a look. So I'm going to change my scale because actually, if I only have, if I had 100 joules, that would only be 4 squares wide, and that's not really going to work for me in this case. I want my graph to be a bit bigger because I want to be able to see a bit more. So in this case, I think what I'm going to go with is 1 square equals, let's go for 10 joules. Okay, because again, it's nice and easy to work with. So, let's have a look. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So my line in this case is, okay, my line in this case is 10 squares, because 10 times 10 is my 100 joules, which is the input. Length of the arrow is not important, so I'm just going to draw an arrow. Now, we can do gaps between these. I'll show you how I would do this. I want 20 joules of light being useful. So I'm going to have an arrow representing 20 joules of light. I've got 10 joules coming out as sound. So I've got an arrow that's 10 joules. and I've got my other arrow there, which is also 20 joules. So 20 joules is 2 squares. Now, in terms of wasted, this arrow needs to be 5 squares wide because that represents 50 joules. So 1, 2, 3, 4, 5. There we go. So we've got this one here. That's 5 squares equals 50 joules of wasted. This is 10 squares going in. That's my total. And that equals 100 joules. And the combined value here is also 5 squares, which equals 50 joules. And all of this should add up. Okay, so we can have a look at the Sankey diagram. I've got my 3 separate arrows. The total width of the arrows should add up to the total width of this one. Okay? Have a look through these, have a look around, and have a practice at making your own up. Like I said, as long as your total output, it matches your total input, it doesn't really make any difference what the values is. But it's well worth having a go at drawing these, because actually it just takes a bit of getting your head around. If you want to, if you can print off some graph paper. There's loads of places online that just do free templates where you can just print off graph paper. And I'll drop this one in as well into the Google Drive for you to use. But watch this video again and have a go at drawing them out so you can actually get used to where you put the pen and pencil and the ruler. So if you do have to do this in an exam, it's not going to be for the first time. And actually, it's one of those things we can come back to and do again later on. So if it's one of those and you're looking at it and you're going, actually, I don't get it, just make a note and we can do it at another point. Okay? Brilliant. So let's move on to the next bit, because we've only got about 14 minutes, 10 minutes left. I think what I'll do is I'm going to leave all the non-renewable and renewable stuff to Friday. So we're not covering too much today. I'll just literally finish off and we'll cut this lesson slightly shorter than some of the other ones. We've spoken about why it's important at homes, but it's not just homes where we really need to worry about efficiency. Any business will be constantly taking in efficiency sort of calculations, efficiency results, and they'll probably have to report it. When I worked in the brewery, we wanted to know that actually how much of the products, the materials that we were buying would end up as the raw materials at the end, because what we didn't want to do is waste it. Now, what we did try and do was use as much of the waste materials for other purposes. So the spent grain that went into making the beer that we used to make would go off a cattle feed. The yeast would then be sent off. Some would go into feed, some of it go into nutrition companies, and some of our breweries that we had up north would end up with the Marmite factory. So that was back years ago. So we tried to make sure that we minimise as much wastage as possible, because everything that's wasted is profit that's lost. Now, that might come down to with electrics as well. So I know some schools, and we're sort of heading that way with the Eco Club that got set up this year, they will try and increase the efficiency of the school by simple things such as turning off lights, turning off computers when they're not on, turning off projectors when they're not on. All of these sorts of things mean that actually the school has to spend less money heating it, providing electrics, which means they have more money to spend on other things. So it's sort of simple things, but actually it has quite a big effect at the end. If you start looking at some of the modern cars, the efficiency has changed massively from some of the older ones. The modern petrol engines, they can get the similar performance, maybe not the torque, but similar performance out of a 1.3 that we used to be looking at with a 1.8 or a 2 litre. And that's because they have managed to make them much, much more efficient in lots of different areas, which means actually you put a lot less energy in to get the same performance back out again. If you go into sports and you have a look at that, one of the reasons why Team Sky did so well is they looked at all the tiny little areas, these little marginal gains, where they could increase efficiency. And by doing that one, they made massive differences over the course, which enabled them to win time in, time out again. So being aware of what efficiency is, being able to use the information to calculate it, and then being able to make decisions based on the data that you get back is really important in pretty much all aspects of life, depending on what you want to do. So don't just look at it and go, this is just for science. This is pretty much going to be used in almost every business, every single industry, everywhere you look in one form or another. And depending on how well you understand it, depends on whether you're going to be able to make the most out of it, save money, make money, or whether it's going to be one of those things you're just going to waste lots, time in, time out. So I'm going to leave it there for now. We've got 10 minutes left, so 10 minutes early today. Friday, we're going to look at renewable and non-renewable energy. If you're stuck on this, you want anything else on it, drop me a line on Google Classroom, drop me an email, and I'll see what I can help. And like I said, if you guys are up for it, I want to do a face-to-face class at some point to go alongside with this, because I think it's something we're going to be doing more of. And actually, it'd be nice. I know you guys are pretty good at, well, it'd be really good to use you guys, as you spent so much time watching these lessons, to actually be the first sort of trial group that we can use with that. So if you're up for it, let me know. Anyway, have a great day, and I shall see you on Friday. Take care.